We are given a ramp, camcorder, a computer program called Logger Pro, a meter stick, and a cart with a piece of felt on the bottom to cause friction against the ramp. With this, we are to find the coefficient of friction within 5% accuracy.
Okay, this is the way we ended up finding acceleration in the x direction down. First, we started with the sum of forces in the y direction equaling mass times acceleration in the y direction down. And then it would be normal force minus weight times cosine theta equals 0. Then the normal force would equal weight times cosine theta. We then did the summation of forces in the x direction equaling max down, giving us w sine theta minus force of friction equaling max down. Weight sine theta minus mu k, normal force, which is force of friction, equals max down. With normal force equaling weight times cosine, we plug that into the equation, giving us weight pulled out equaling sine theta minus mu k cosine theta equaling max down. We then substituted mg for weight, causing the masses to cancel, which would equal g times sine theta minus mu k cosine theta equaling the acceleration of the x in the down direction, giving us the final equation of acceleration in the x down the ramp equaling g times sine theta minus mu k cosine theta. Now here's the equation for the acceleration of the x direction up the ramp. We again started with the forces in the y direction equaling mass times acceleration in the y equaling normal force minus weight cosine theta equals 0. Normal force equaling weight times cosine theta again. We then again did some of the forces in the x direction equaling max in the up, which equaled w or weight sine theta plus friction, force of friction, equaling mass times acceleration in the x direction up the ramp. Substituting mu k in again for force of friction, we got w sine theta plus mu k in equals max in the up direction. With substituting normal force for weight cosine theta, we pulled the w out again, equaling w times sine theta plus mu k cosine theta equals max in the up direction. Making weight equal mg again, the masses again canceled, making the equation g times sine theta plus mu k cosine theta equals the acceleration in the x up direction, giving us the end equation of acceleration in the x direction up the ramp equaling g times sine theta plus mu k cosine theta. Okay, with the two equations that we got, the acceleration in the x direction up the ramp and acceleration of the cart down the ramp in the x direction, we then use system of equations to cancel out some stuff. So then we're going to do acceleration in the x direction up minus the acceleration in the x down equaling g sine theta plus g mu k cosine theta minus g sine theta minus g mu k cosine theta. Getting the g sine thetas to both cancel and everything else stays. So then it would equal acceleration of the x direction up the ramp minus the acceleration in the x direction down the ramp equaling 2g mu k cosine theta. With moving stuff around, we end up getting mu k equaling acceleration of the x up the ramp minus acceleration x down the ramp divided by 2g cosine theta.
This is the video of our cart going down. We uploaded it to the computer and trimmed it and then put it in Logger Pro. In Logger Pro, we tracked the cart on the ramp. Logger Pro plotted the points and gave us put it on a position time graph and gave us an equation. And this is the video of the cart going up. We uploaded it to the computer and trimmed it, put it in Logger Pro, tracked the cart on the ramp, and Logger Pro plotted the points and gave us our position time graph again and the equation.
Okay, so to find the acceleration in the x-axis going up, we found that to be 0.9764 meters per second squared. And the way we found that was through Logger Pro. And what Logger Pro does is it helps us find the position function, which is a quadratic. And by taking the second derivative of that, we're able to find the function for acceleration. So that's how that came out to that. And we can also use that to go to the acceleration in the x-axis going down for when the cart's going down. And we find that to be negative 0.792 meters per second squared. I mean, we just did the same thing. And I mean, obviously, the gravity is a constant at 9.8 meters per second squared. And the way we found theta is by actually measuring the distance of the ramp and the distance of the table from the start of where we started the cart to the intersection of those 2 points, and taking the arc cosine of the distance of the table over the distance of the ramp. And by finding that, we found 4.43 degrees. And when we get all those numbers, we plug it in for the coefficient of friction, which is the acceleration in the x-axis going up minus the acceleration in the x-axis going down. All of that divided by 2 times gravity times cosine of theta. And we found that to be 0.0905. So our conclusion is that we plugged in our accelerations back into acceleration equations, find the coefficient of friction for each equation. The coefficient for friction for acceleration on the x-axis going down was 0.16, and the coefficient for acceleration in the x-axis going up was 0.02, causing the relative uncertainty to be equal to plus or minus 0.07. With that, we calculated the coefficient of friction to be 0.0063% correct.